For this problem, we have to find which groups have an odd number of shapes. So first we can count the amount of shapes in each of the groups. So in group A, there are 7 shapes. In group B, there are 6 shapes. And in group C, there are 9 shapes. So we know that odd numbers cannot be divisible by 2, so they must end in a 1, 3, 5, 7, or 9. So looking at these groups, only group A and group C end in one of these 5 numbers. So the answer to this problem is group A and group C. For this problem, we have to figure out which two numbers added together result in an even number. So we could use trial and error in this problem, but we know that when we add an even with another even number, we always get an even number. But when we add an even and an odd number, we always get an odd number. Only when we add an odd number and an odd number, we get an even number. So looking at the numbers we have here, we know that 4 is even, 5 is odd, and 6 is even. So we can add an even number and an even number to get an even number. So in this case, we would add 4 and 6. So the answer to this problem would be 4 and 6. For this problem, we have to figure out which two groups of shells, when put together, would result in an even number of shells. So first we can count the amount of shells in each of the groups. So for group X, there are 5 shells. In group Y, there's 6 shells. In group Z, there are 4 shells. So like I mentioned in the last problem, we know that an even number plus an even number would give us an even number. So in this case, we know that 5 is odd, 6 is even, and 4 is even. So we can do 6 plus 4, and that would give us an even number of shells. So in this case, the problem is asking which two groups of shells would give us an even number. So that would be group Y and group Z. For part A of this problem, we have to find the number of odd numbers between 2 and 10. So this is really straightforward, as we can just list them out. So that would be 3, 5, 7, and 9. So that gives us 4 numbers, so the answer to part A would be 4 odd numbers. So for part B of this problem, we have to find all other pairs of even numbers which have the same number of odds as between 2 and 10, and we are only allowed to use counting numbers less than 15. So in order for the pairs of even numbers to have the same odds as between 2 and 10, they must have the same difference as 2 and 10. So we can first find the difference of 2 and 10 by doing 10 minus 2 to get 8. So the pair of even numbers must have a difference of 8. Since 2 is the smallest even counting number, we can only add on to 2 and 10. So we would do 2 plus 2 to get 4, and 10 plus 2 to get 12. So one of our pairs of even numbers would be 4 and 12, as there is a difference of 8. And we can continue that process by adding 2 to 4 to get 6, and 12 to 2 to get 14. So another pair would be 6 and 14. And this is our last pair, because if we add 2 to 14, we would get 16. And 16 is bigger than 15. So our answer is 4 and 12 and 16 and 14. For part A of this problem, we have to find out if Harry and Maya can split the cubes on the right evenly. So first we can count the number of cubes, and we get there are 7 cubes. And since 7 divided by 2 does not result in a whole number, they cannot split the cubes evenly, so the answer to part A would be no. For part B of this problem, we have to figure out how many ways Harry and Maya can share the cubes. Since they are sharing the cubes, each of them must have at least one. So we can make a table to help solve part B. So when Harry has 1 cube, Maya has 6 as these add up to 7. Harry has 2, Maya has 5. Harry has 3, Maya has 4. When Harry has 4, Maya has 3. When Harry has 5, Maya has 2. And when Harry has 6, Maya has 1. So we can count these up and we get that there are 6 ways Harry and Maya can share the cubes. So the answer to part B would be 6 ways. For part A of this problem, we have to find the largest 2-digit even number that uses the digit 9. And since 9 is an odd number, it has to be our first digit. As even numbers can only end in 0, 2, 4, 6, or 8. And out of these 5 numbers, 8 is the largest number, so 98 would be our answer to part A. For part B of this problem, we have to find the largest 2-digit even number that uses the digit 3. Since 3 is odd, it would be our first digit. Our second digit is 8 because it is the largest even number possible for the units digit. So our answer to part B would be 38. For part C, we have to find the largest 2-digit number that we can split evenly into 2 parts. So that means the number must be even. So we can take the smallest even 3-digit number and subtract 2 to get 98. And that is our biggest even 2-digit number. So the answer to part C would be 98. For this problem, we have to find the number of candies Francine and Kevin have. We know that if they split the candy evenly, they will have 1 left over. So if x is the number of candies, we know that when x is divided by 2, there is a remainder of 1. We also know that if they split with their friends Sasha, Sid, and Lisa, there will be 2 left over. So we know that when x is divided by 5, there is a remainder of 2. From this information, we can find numbers that might work. For example, we can take a multiple of 5 and then add 2, and that would satisfy our second condition. So the numbers between 40 and 55 that satisfy the second condition would be 42, 47, and 52. So now we have to look at our first condition, that when x divided by 2, the remainder is 1. When 42 is divided by 2, the remainder is 0. When 47 is divided by 2, the remainder is 1. And when 52 is divided by 2, the remainder is 0. So out of these 3 numbers, only 47 meets our requirements. So thus, 47 is the answer to this problem. For this problem, we have to add symbols between 4 fours to get 9. All of the numbers we are given are even, but we're trying to get an odd number. And the only way to do that in this case would be to do 4 divided by 4, and that would give us 1. So our equation would look something like this. And now we have to just find these 2 signs. Since we know 4 divided by 4 is 1, we can just add 4 twice to get 9. So we can plug in addition signs here, and this would be our answer. For this problem, we have to find the value of the Egyptian numbers, so we can just do this by plugging in the numbers for the symbols. So for part A, we would do 100 plus 10 plus 10 plus 3 plus 100 plus 10 plus 10 plus 4, and that would give us an answer of 247. For part B, we can do the same thing. So that would be 100 plus 100 plus 100 plus 10 plus 10 plus 4 plus 100 plus 100 plus 10 plus 10 plus 10 plus 10 and plus 9. So that would give us a sum of 573, and that's our answer to part B. For this problem, we have to find the mystery number using the clues that we are given. We know that the number has 2 digits. Both of the digits are even. The digit in the tens place is greater than the digit in the ones place. The sum of 2 digits is a multiple of 5, and the tens digit is 2 more than the ones digit. From the first 2 clues, we know that the first digit can be 2, 4, 6, or 8, and the second digit can be 0, 2, 4, 6, or 8. From the last clue, we can narrow down our numbers to 20, 42, 64, and 86, since the tens digit is 2 more than the ones digit. Our fourth clue says that the sum of the two digits is a multiple of 5, so we can add up the digits in each of these numbers. So 2 plus 0 is equal to 2, 4 plus 2 is equal to 6, 6 plus 4 is equal to 10, and 8 plus 6 is equal to 14. So out of these four numbers, only 10 is a multiple of 5, so the answer to this problem would be 64. For this problem, we have to find numbers that satisfy the statements. For part A, we have to find the smallest number that is a multiple of 5 and is even but not a multiple of 4. So we can approach this problem by listing out some multiples of 5 and then testing them to see if they satisfy Ben's statement. So I'm going to list out some multiples of 5. So now we can start from the beginning and start testing them to see if they work. So 5 is not even, so does not work. 10 is even, and it is not a multiple of 4, so 10 works. So the answer to part A would be 10. For part B, we can use a similar approach because we're trying to find the smallest number that is a multiple of 5 and 3, but not a multiple of 9. So we can start from the beginning and start testing the numbers. So 5 is not divisible by 3, so it does not work. 10 is also not divisible by 3. 15 is divisible by 3, and it is not a multiple of 9, so 15 works. So in this case, the answer to B would be 15. We can use this approach to find the smallest number that satisfies all of these statements. 5 does not work because it is not even. 10 doesn't work because it's not a multiple of 3. 15 doesn't work because it's not even. 20 doesn't work because it's divisible by 4. 25 does not work because it is not even. And 30 satisfies all three conditions, so the answer to part C would be 30. For this problem, we have to find the value of A plus B plus C plus D plus E. To do this, we must find the numbers that go in this row and this column. To find these numbers, we can first find a common factor of 15 and 18. In this case, the only common factor between 15 and 18 is 3, so 3 would go here. 15 divided by 3 is 5, so 5 goes here. 18 divided by 3 is 6. 40 divided by 5 is 8. 60 divided by 6 is 10. 20 divided by 10 is 2. 10 divided by 2 is 5. 20 divided by 5 is 4. 24 divided by 4 is 6. And 56 divided by 8 is 7. So let's start off with A. A is 2 times 3. B is 5 times 5. C is 6 times 8. D is 4 times 10. And E is 7 times 6. We can then find the product of each of these numbers. So 2 times 3 is equal to 6. 5 times 5 is 25. 6 times 8 is 48. 4 times 10 is 40. 7 times 6 is 42. And now we can add up these 5 numbers to get our answer. So 6 plus 25 plus 48 plus 40 plus 42 is equal to 161, which is our answer. For this problem, we have to use the cards below to make a number that satisfies the condition. So for part A, we have to make a number between 6.1 and 6.81. Our first digit has to be a 6, because if it was an 8 or a 1, it would not be between 6.1 and 6.81. So that leaves us with two options, 6.18 and 6.81. So out of these two options, only 6.18 is between 6.1 and 6.81. So our answer to part A would be 6.18. For part B, we have to make the largest possible number that is less than 7. So out of 1, 6, and 8, the largest number that is less than 7 is 6. So our first digit is 6. Our second digit is 8 because 8 is greater than 1. So that leaves us with 1, which is our last digit. So the answer to part B would be 6.81. For part C, we have to make the largest number possible. 8 is our biggest number, so 8 will be our first digit. Our second digit is 6 because 6 is greater than 1. So our last digit is 1. So the answer to part C would be 86.1. For number 14, we have to figure out what number the letter A stands for. So when a number is divisible by 9, we know that the sum of the digits is also divisible by 9. That means A plus 3 plus 4 plus 6 plus A is a multiple of 9. We can simplify that to get 2A plus 13 is equal to a multiple of 9. So now we can start testing multiples to see if they work. The smallest multiple of 9 that is greater than 13 is 18. So we can set the equation 2A plus 13 is equal to 18. And we subtract 13 from both sides to get 2A is equal to 5. And that gives us A is equal to 2.5. 2.5 has a decimal, so it will not work in this instance. So we can try the next multiple of 9. So we can set the equation 2A plus 13 is equal to 27. We can subtract 13 from both sides to get 2A is equal to 14. Now we can divide both sides by 2 to get A is equal to 7. Since 7 is a single digit and is not a decimal or fraction, it works in this instance. So the letter A stands for 7. For this problem, we have to figure out how many positive numbers less than 20 cannot be written as the sum of two prime numbers. We know that 2 is the smallest prime number and the only even prime number, so anything less than 2 plus 2 cannot be written as the sum of two prime numbers. So 2 plus 2 is equal to 4. So all the numbers under 4 cannot be written as the sum of two prime numbers. So that would be 1, 2, and 3. Like I mentioned, 2 is the only even prime number, so we must use 2 when testing the odd numbers because the only way to obtain an odd sum from two numbers is an odd plus an even, and 2 is our only even prime in this instance. So the only way to obtain an odd number is to do 2 plus an odd number. Now we can begin testing the odd numbers greater than 4. So 5 is equal to 2 plus 3, 7 is equal to 2 plus 5, 9 is equal to 2 plus 7, 11 is equal to 2 plus 9, 13 is equal to 2 plus 11, 15 is equal to 2 plus 13, 17 is equal to 2 plus 15, and 19 is equal to 2 plus 17. Our final test is to see if the numbers in this column are prime, because if it is not prime, then the numbers here cannot be written as a sum of two prime numbers. So let's start from the first row. 3 is prime, 5 is prime, 7 is prime, 9 is not prime, 11 is prime, 13 is prime, 15 is not prime, and 17 is prime. So this means 11 and 17 cannot be written as a sum of two prime numbers. So our answer to this problem would be 1, 2, 3, 11, and 17. For this problem, we have to put operation signs and parentheses if needed between the numbers 3, 4, 5, and 6 to make the highest possible number and the lowest possible number, and we can only use each sign once. We know that the addition and multiplication sign increases the number, while the subtraction and division sign decreases the number. So when we are trying to get the highest possible number, we want to use the multiplication sign, the addition sign, and one of these signs. So since multiplication increases the number by the most, we want to use it with our biggest number, which is 6. So we'd have some number here times 6. So now we want to use the addition sign, which is the only other sign that would increase our number. So we would use it with the next two largest numbers, which are 5 and 4. So now we have to use one of these signs, which would decrease our number, and we can test both of them out. So first we can do 5 plus 4 times 6. So that would be equal to 9 times 6, which is equal to 54. So now we can do 54 minus 3 is equal to 51, and 54 divided by 3 is equal to 18. And since 51 is larger than 18, 51 would be our answer to part A. So for part B, we're trying to find the lowest possible counting number. So in this case, we would use both of the signs that would decrease our number and one that would increase our number. So we would want to use our division sign with 6 because it would decrease 6 by the most. So we can do 6 divided by 3. So next we want to use the remaining sign that would decrease our number with the largest number left, which would be 5. So we would subtract 5 here. And then finally we can add 4 to get 1, which is our lowest possible counting number. For this problem, we want to find at least one way to place the operation signs and parentheses if needed to make the following digits become 100. So you can solve this problem by using trial and error, but I'm going to show you how I would approach this problem. First, I would assume all of the numbers have an addition sign between them, so I can see how far away the sum is from 100. After I add these numbers up, I'll get 45, which is 55 less than 100. So I have to find a way to increase this by 55. One way we can do that is by replacing the addition signs between these digits by multiplication signs. So we can start off by replacing the addition sign between 8 and 9 with the multiplication sign. So we're replacing 8 plus 9 with 8 times 9. So removing 8 minus 9 would cause our number to decrease by 17, but adding 8 times 9 would cause our number to increase by 72. So that would cause a total increase of 55, which happens to be the amount that we needed to get to 100. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 times 9 is equal to 100. So this is one of our possible answers. For this problem, we have to find how many two-digit primes between 10 and 99 have the property where its reverse is also prime. Any prime number greater than 10 can only end in 1, 3, 7, or 9, because if it ends in 5, it is divisible by 5. So now we can begin writing prime numbers that are made using these digits. So 11 is prime, 13 is prime, 17 is prime, 19 is prime. 31 is already repeated above, it's the inverse of 13. 33 is not prime, 37 is prime, 39 is not prime. The reverse of 71, which is 17, is already here. The reverse of 73, which is 37, is already here. 77 is not prime, and 79 is prime. All the other numbers beginning with 9 are either not prime or the prime inverse is already here. So now we can test to see if the reverse of these numbers are also prime. The reverse of 11 is 11, which is prime. The reverse of 13 is 31, which is prime. The reverse of 17 is 71, which is prime. The reverse of 19 is 91, which is not prime. The reverse of 37 is 73, which is prime. And the reverse of 79 is 97, which is prime. Now we can count the number of numbers we have, and there are 9. So the answer to this problem is there are 9 two-digit primes that are between 10 and 99, which have the same property.